In this video, I'm going to go over how to set up a flip sim with a high poly geometry as the collision environment. This is the second part to a beginner video for the flip simulation, which covers more of the basics. So if you're a beginner and completely new to flip simulations, you may want to check that video out first. A link will be posted in the description below. In this video, you'll hear me refer to the first example quite a bit, because the recording was all done all at once with both videos. But don't worry, I display screenshots from the first video for viewing convenience and clarity, so you should be fine if you already know the basics of the flip sim. Here's a brief overview of the topics for this video. We'll go over setting up the fluid emitter and controlling the amount of emission. Next, we'll improve on collision detection for the sim and configure a proxy volume for the flip solver for a more accurate representation of the geometry. Last, I'll discuss how to build up from a simple Houdini scene to a more complex scene, using the first beginner video as an example for the comparison. I'm going to move on to a more complex example for the flip simulation. Instead of just having a ground colliding with the fluid in the previous example, I'm going to be using this ruined castle geometry. This is what it looks like rendered out. So this castle geometry is a lot more complex than that simple ground that we were using before, which was just a plane. This is what the ruined castle looks like in terms of the nodes that I used. So there's a lot of pieces to it. There's like a spiral castle, the arc door, pillars, and a fractured ground. I'm not going to be going over how I made the castle because that's beyond the scope of this video. These three nodes are the ones that we're going to mainly focus on for this video. So let's take a look at what the sim looks like. So this should be very familiar to you if you watched the previous example. There's an emitter, which is this part. I'm going to highlight in red. So this is the emitter, which was the box emitting all the water fluid in the previous example. Then we have the simulation data. This is just the .net and the .import. Then we convert all the simulation data into a geometry, which is what this is, the water geometry. So we can render it out. We can attach a material to it and render it out. So let's start with the emitter and take a look at what it looks like. So I started off with just a box, which is very similar to what we had before in the previous example. I position it so that it's right at the top of this spiral staircase, and the water is going to flow down through these staircases, down this walkway, and out through this hole that I fractured out of the spiral staircase, out of the wall. So it's going to flow right out here and land on the ground. Then I made the box a little smaller. Now this is where it gets a little more interesting. I tell Houdini to fill this box with points, and that's what this node does, points from volume. It fills it with all these points. For the point separation parameter, the lower this number, the more points it's going to fill. This point separation is the gap between points. So obviously, the lower the distance of the gap, the more points you can fit in this box. So we didn't have this, I didn't use this node in the previous example. This is a way to control how much fluid you want to emit from the box. So obviously more points means more fluid. I take all the points and I feed it into the VDB from particle fluid. So what this does will give me a fluid density volume. I take that and I finally feed it into the flip source, which is the same flip source that was used in the previous example, which will generate the surface volume. And that's all for the emitter. So let's go back to the sim. Now the box is here. So we have our volume, box emitter, that has the surface volume. We feed that into the .NET. I'm just gonna go to frame 1 so it doesn't start cooking. Let's go inside. Now this setup is very similar to the previous example. We have the flip object, which is what is the initial body of water that we want to start off with. And I'm not going to be starting off with anything. I'm going to be sourcing the water from that box emitter and constantly flow water out of it like a faucet. So that's why we have the volume source. I turn that surface density that was generated from the previous, here I'll show it, from this box, which had the surface volume. And I'm going to use that surface volume and I want to convert it into density so that the flip solver can make sense of it all. Something weird happened to my viewport. So when you see this, just open up a new scene view tab. So the flip solver, I don't think I changed much parameters in here. The only thing I can think of changing is the max subsets. It defaults to 2. I lowered it to 1 because the simulation was taking forever to calculate. And the volume limits in the flip solver, I made the box a little smaller, so it would optimize the simulation a little bit, because I don't need water outside of this box. Like, water's not gonna be sprouting above this level, above this line right here. So this is the limit of the simulation. That's what I'm telling Houdini. So it doesn't have to work as hard and calculate as long. Now this is the static object. We used to have a ground that we had attached here. And this was just a plane. Now we have a castle, a more complex geometry to collide with. So this castle, this is what it looks like. This is what it's going to look like. This is the geometry that we're going to use to render with. However, this is not what it's colliding with. This is the geometry that it's colliding with. So this is, now this is what we specify to have the flip solver collide with. Let's go into this colliding geometry. Let's take a look. So these are all the pieces of the castle. This is just what, for rendering, or this is for display purposes. Now, some of this geometry, it's really thin, and it's really hard for the flip solver to calculate collisions with. It's because it's too thin. Water's just gonna go berserk, and it's not gonna have a hard time calculating the collisions. So in order to fix that, you have to make it a little thicker. I'm gonna show a few pieces of how I made the geometry a little thicker for the simulation, to help the simulation calculate the collision. Let's take a look at the doorway. So this is the arc doorway. As you can see, this is too thin. It's not gonna have a good time calculating it. So we need to fill in all this gap here and that will tell the flip simulation that water shouldn't pass through here. This is a solid. I threw down a clip in order to get rid of the back part because the camera's facing this side. Then I extrude the volume to make it a lot thicker. Let's zoom in here. So then after I made it thicker, it goes into a point from volume. So I fill this solid with points all over. Oops. I fill this solid with points. And just like the box emitter, I throw down a VDB from particle fluid node, which will turn it into a volume. Since this castle has a lot of pieces, I take all the pieces that I made thicker and I merged it all together. So this is what you get. Sorry, this is what you get. We no longer have that thin piece on the back. Everything's really thick and definitely a solid. Making the geometry thicker will allow us to create an accurate volume representation of the geometry, which has the SDF information, so the solver will know if the water is getting closer to the geometry and make the decision of when the water collides. You can merge all the polygons together, so it doesn't have to be a Boolean merge. As long as you just merge it, the geometry can still be separate, but just merge it together in one node. Then throw down the points from volume to put points all over the solid. Now the point separation for the points from volume is set very low. So once I hit this render flag, it'll cook forever. So I don't want to hit it right now, but I did file cache it, so this will load a lot quicker. So I can show you this. So this is what it looks like after you throw in the points and after you throw in VDB from particle fluid to convert it into a volume. You have all this thickness and you have a general shape of what the original castle looks like. So let's go back to the simulation and see how we can use this proxy volume. Now back to the simulation, back into the .NET. The SOP path that we choose is just the display geometry. So this is not what it's colliding with. Since this is a very complex geometry, I need to tell it, don't use this path, this SOP path. I want to use a different, more detailed geometry to calculate the collisions. For under the collision tab, RBD solver, the collision detection, there's a use volume collisions. it defaults to surface collisions, which was what was used in the previous example, but I want to use the volume collisions because my proxy geometry is in a volume format. You can check this collision guide in order to see what is actually the geometry being collided with the water. But remember to uncheck the display geometry. Otherwise, you'll be wondering, where's my blue in the viewport? Because the display geometry and the collision guide may overlap, and usually the display geometry is the one going to be displayed in the viewport, and you won't see this blue. For the mode, choose volume sample because we're sampling from the proxy volume. So the proxy volume is linked to my proxy VDB, which is this guy, which is the one with the huge VDB that I put down, that I file cached. So that's all you need to do to set up the proxy volume to improve the collision detection. Just hit play and start cooking the sim. Very similar to the previous example. The reason why I started with the simpler example and try to build it up into a more complex one, it's a lot easier if you start with something that works and it's simpler. One, the PC loads a lot faster and you can test that your logic works. So this is the very simple example I started off with. In the more complex sim, the ruined castle replaces the ground plane. So I added a static object instead of adding a ground plane. And I had it all set up with the castle. And all I did was merge it, just like before. So it goes left to right. And then that is this setup. Then I drop down the all familiar dot import node, which takes all that simulation data and brings it into the attribute setup. So if we have a .net here, this is the data that we're getting, which is not very useful for us for rendering. So we need it in the geometry spreadsheet. We can see we have the attributes and the familiar table that we're used to. Now I added a file cache right after the dot import. You don't have to do this. I only did it because for filming purposes, it just made it easier to show you what the simulation looks like. Actually, I can. So this is what it looks like. So you can see all the particles coming down. Then I added a fluid compress node. Now this compresses all the simulation data, so it has less data here. It makes it more compact. But if I put a render flag here, it's not gonna render correctly because it's missing a lot of data. You have to rebuild it. Now that's what the particle fluid surface is good at doing. It's good at reading this fluid compress node, all the data that comes out of it. These two nodes go hand in hand together. So if I put this here, I'll put the render flag here. Now it converts it into a solid for us. It converts the fluid into something, into a solid, into points, into surfaces, into primitives, so we can render. We have something that we can attach a material to and render it out. So I drop down a file cache right after this. Now this is where you should use a file cache, right after you convert the particle fluid surface, because it takes a long time to cook the simulation and convert it into a surface that you can actually render with. So you really need to file cache it. So this is what it looks like after it's rendered out with the fluid on frame 136. So this is what it looks after I rendered the full animation out. And now I added a background with the same animation. Now if you recall, I said the point in the emitter, that's that box emitter that we put down, and we had a point from volume. So that's this box at the top of the staircase. At the top of the spiral staircase. That's this box. In the box emitter, the more fluid flows down. So right now I have my point separation is 0.015, which has resulted in 28,860 points. So that was a lot more fluid flowing in my simulation compared to what I had before in the previous sims that I did to try out. Now I cached that one out just to show you what it would look like with less water. So this is the blue one here. So this is cached out. So it's a lot less. It's the same frame. So this is how much fluid is coming out. This is what it looks like after it's converted into a mesh. By increasing the emitter's points, so increasing this value, which will generate less points as a result for this box emitter, I was able to source less water in my simulation. If I remember correctly, to get this scene with less water, I cooked the sim at 0.1 point separation. So this is what the animation looks like after it's rendered out. By playing with the point separation value from the points from volume node, you can generate very different effects. On the left, larger the point separation, less points, less water. On the right, smaller the point separation, more points, more water. I hope you enjoy this two-part video series on flip simulations. If you have any tutorial suggestions, feel free to post a comment. I might not get to it right away. Please be patient because these videos take a very long time to produce, with research, asset preparation, recording, and even editing, which takes a load of time to produce. I hope I can get faster at this as I do more of these and get more familiar with the filming process. Thanks for watching and sticking all the way to the end of the video.